What if the stars were no longer out of reach? What if crossing the vast expanse of space took weeks instead of centuries? The future of space travel hinges on one critical factor: propulsion. Today, we're diving into 30 next-generation technologies that could completely redefine how we explore the cosmos. From ion drives that silently propel spacecraft through the void to antimatter engines that harness the energy of the universe itself. These breakthroughs are poised to turn science fiction into reality. Why does this matter? Because the way we move through space will determine how far we can go and how quickly we can get there. This isn't just about faster rockets, it's about unlocking the potential for humanity to become an interstellar species. So, buckle up as we explore the cutting-edge innovations that could shape the future of space exploration and take us closer to the stars than ever before. Space exploration stands at a pivotal moment in history. For decades, chemical rockets have been our workhorses, carrying satellites into orbit and astronauts to the moon. But as we set our sights on destinations like Mars, the outer planets, and even neighboring star systems, the limitations of these traditional systems become glaringly apparent. Chemical propulsion is powerful, yes, but it's also incredibly inefficient. Think of it like driving a car that guzzles fuel at an astonishing rate, only to travel a few miles before needing to refuel. In space, that inefficiency translates to enormous costs, limited payloads, and missions that take years or even decades to complete. The challenges don't stop there. Chemical rockets rely on finite resources like liquid oxygen and hydrogen, which are not only expensive to produce, but also difficult to store for long-duration missions. Plus, the sheer weight of the fuel needed to propel a spacecraft means less room for scientific instruments, life support systems, or even the astronauts themselves. It's a problem that's holding us back from exploring deeper into the cosmos. But here's the exciting part: the solutions are already taking shape. Next-generation propulsion technologies promise to overcome these limitations, offering faster, more sustainable ways to travel through space. Imagine spacecraft that don't need to carry massive fuel tanks or engines that can run for years on just a few grams of propellant. These innovations aren't just about speed, they're about efficiency, sustainability, and unlocking the potential for humanity to become a truly spacefaring civilization. The road ahead is undeniably challenging. Developing these technologies requires breakthroughs in physics, engineering, and materials science, but the opportunities are equally immense. With the right propulsion systems, we could cut travel times to Mars from months to weeks, explore the icy moons of Jupiter and Saturn, and perhaps one day send probes to nearby star systems. It's not just about reaching new destinations, it's about transforming how we think about space travel altogether. So, what does the future hold? Let's begin our journey into the first of 30 groundbreaking propulsion technologies that could redefine our place in the universe. This isn't just about building better rockets, it's about opening doors to possibilities we've only dreamed of, and it all starts with rethinking how we move through space. Let's shift our focus to a technology that's already making waves in space exploration: ion drives. Picture this: a spacecraft gliding silently through the void, propelled not by roaring flames, but by the gentle push of charged particles. This isn't science fiction, it's the reality of ion propulsion, a technology that's quietly revolutionizing how we travel through space. Already proven in missions like NAS, a Dawn spacecraft, which explored the asteroid belt, ion drives are the unsung heroes of next-generation propulsion. So, how do they work? At their core, ion drives use electric fields to accelerate ions charged particles to incredibly high speeds. These ions are expelled from the engine, creating a steady, continuous thrust. Unlike the explosive bursts of chemical rockets, ion drives provide a gentle but relentless push, like a marathon runner pacing themselves for the long haul. While the thrust is low compared to traditional engines, the efficiency is staggering. Ion drives can operate for years on just a few kilograms of fuel, making them perfect for missions that require endurance over raw power. This efficiency opens up incredible possibilities. Imagine sending a probe to the outer reaches of our solar system without the need for massive fuel tanks. Ion drives are already enabling missions to distant asteroids, comets, and even dwarf planets. They're the ideal choice for deep space exploration, where the ability to sustain thrust over long periods is far more valuable than short bursts of speed. But ion drives aren't just about efficiency, they're also about precision. Their gentle thrust allows spacecraft to maneuver with incredible accuracy, making them invaluable for missions that require delicate adjustments, like orbiting distant celestial bodies or maintaining position in deep space. This combination of endurance and precision makes ion drives a cornerstone of future exploration, offering a way to reach destinations that were once thought too distant or impractical. Of course, no technology is without its challenges. The low thrust of ion drives means they're not well suited for missions that require quick acceleration, like launching from Earth's surface or landing on a planet. But for the vast, open stretches of space, where time is less of a constraint, they shine. As we look to the future, ion drives could play a critical role in missions to the outer solar system, from studying the icy moons of Jupiter and Saturn to exploring the mysterious Kuiper belt. And who knows, they might even pave the way for our first interstellar probes, carrying humanity's curiosity to the stars. This is the beauty of ion propulsion. It's a reminder that sometimes the journey to the stars begins not with a bang, but with a steady, silent push. It's a testament to the power of patience and persistence, qualities that will be essential as we venture further into the cosmos. Now, let's turn up the heat literally and explore a propulsion system that takes ion drives to a whole new level: plasma propulsion. Imagine a rocket engine that doesn't rely on burning fuel or even simple ions, but instead taps into the raw power of plasma, the fourth state of matter. This isn't just a step forward, it's a leap into a new frontier of space travel, one that could redefine how we think about speed, efficiency, and the very nature of propulsion. So, what exactly is plasma? Think of it as a supercharged gas, where atoms are stripped of their electrons, creating a soup of charged particles. It's the same stuff that makes up the sun and lightning bolts here on Earth, a fiery, energetic substance that's as powerful as it is unpredictable. And now, scientists are harnessing this power to create engines that could take us farther and faster than ever before. Enter the Wassermann engine, short for Variable Specific Impulse Magnetoplasma rocket. This cutting-edge technology uses magnetic fields to heat plasma to extreme temperatures, creating thrust by expelling it at incredibly high speeds. Unlike traditional chemical rockets, which burn fuel in a single explosive burst, or even ion drives, which offer steady but modest thrust, Wassermann combines the best of both worlds. It can adjust its power output on the fly, delivering high thrust when needed or switching to a more efficient, low-thrust mode for long-duration missions. It's like having a sports car and a hybrid in one: flexible, powerful, and built for the long haul. The implications for space travel are staggering. With plasma propulsion, a mission to Mars could be cut from months to just weeks. Imagine astronauts spending less time exposed to the dangers of deep space and more time conducting groundbreaking research on the red planet. And it doesn't stop there. Plasma engines could make missions to the outer planets like Jupiter's icy moon Europa or Saturn's rings far more feasible, opening up new possibilities for exploration and discovery. But as with any groundbreaking technology, there are challenges to overcome. Plasma propulsion requires immense amounts of energy, which means spacecraft would need advanced power sources, like nuclear reactors or massive solar arrays. Then there's the issue of heat. Plasma is incredibly hot, and managing that heat without melting the engine is no small feat. Scaling up these systems for interstellar travel adds another layer of complexity, as the distances involved are orders of magnitude greater than anything we've tackled before. Yet, despite these hurdles, the potential is too great to ignore. plasma propulsion represents a paradigm shift in how we approach space travel, offering a path to faster, more efficient missions that could take us to the far reaches of our solar system and beyond. It's a reminder that the future of propulsion isn't just about building better engines, it's about reimagining what's possible when we harness the raw power of the universe itself. As we look ahead, plasma propulsion stands as a testament to human ingenuity and our relentless drive to explore the unknown. It's a technology that's as bold and dynamic as the cosmos it seeks to conquer, and it just might be the key to unlocking the next chapter of space exploration. Now, let's step into the realm of nuclear thermal propulsion, a technology that takes the raw power of the atom and channels it into the heart of a spacecraft. Picture this, a rocket engine that doesn't rely on burning chemicals, but instead uses the immense energy released by splitting atoms to generate thrust. It's a concept that might sound like it's straight out of a sci-fi novel, but it's very much grounded in real-world science, and it could revolutionize how we travel through space. At its core, nuclear thermal propulsion works by harnessing the heat produced during nuclear fission. Here's how it plays out. A reactor splits uranium atoms, releasing a tremendous amount of energy in the form of heat. This heat is then used to superheat a propellant, typically liquid hydrogen, turning it into a high-speed gas that's expelled through a nozzle to create thrust. The result, a propulsion system that's far more efficient than traditional chemical rockets, capable of delivering more thrust with less fuel. What makes nuclear thermal propulsion so exciting is its potential to dramatically reduce travel times. Imagine cutting the journey to Mars from 6 months down to just 3. For crewed missions, this is a game changer. Shorter travel times mean less exposure to the hazards of deep space, such as cosmic radiation and the psychological toll of long-duration isolation. It also means astronauts could spend more time conducting meaningful research on the Martian surface and less time in transit. This isn't just about speed, it's about making space exploration safer, more efficient, and more sustainable. But let's not gloss over the challenges. Safety is a critical consideration when dealing with nuclear technology. Space agencies must ensure that reactors are designed to withstand the rigors of launch and operate reliably in the vacuum of space. There's also the question of how to manage radioactive materials, both during the mission and after the spacecraft's lifespan. Fortunately, modern engineering and rigorous safety protocols are making these challenges more manageable, paving the way for nuclear thermal propulsion to become a viable option for future missions. Another advantage of this technology is its scalability. Unlike some propulsion systems that are limited to specific types of missions, nuclear thermal engines can be adapted for a wide range of applications. From crewed missions to Mars to robotic probes exploring the outer planets, the versatility of this system makes it a top contender for near-future exploration. And let's not forget the potential for lunar missions, where nuclear thermal propulsion could support the establishment of a sustainable human presence on the Moon. Of course, public perception plays a role too. The word nuclear can evoke concerns, but it's important to emphasize that the risks are carefully managed. The reactors used in space are vastly different from those on Earth, designed with fail-safes and redundancies to ensure safety. By demystifying the technology and highlighting its benefits, we can build the public support needed to make nuclear thermal propulsion a reality. As we look to the future, it's clear that nuclear thermal propulsion has the potential to be a cornerstone of space exploration. It's a technology that bridges the gap between the familiar and the futuristic, offering a practical yet transformative way to push the boundaries of what's possible. By unlocking the power of the atom, we're not just building better engines, we're opening the door to a new era of discovery, where the solar system becomes within reach like never before. Now, let's explore a propulsion system that merges the best of two worlds, nuclear electric propulsion. Imagine harnessing the immense energy of a nuclear reactor to power the precision and efficiency of ion drives. It's a combination that sounds almost too good to be true, yet it's a concept that's already being developed, and it could be the key to unlocking the outer reaches of our solar system. So, how does it work? At its heart, nuclear electric propulsion relies on a nuclear reactor to generate electricity. This electricity then powers ion engines, which use electric fields to accelerate ions and produce thrust. Think of it as a hybrid car, where the nuclear reactor acts like a high-capacity battery, providing a steady stream of energy to keep the ion engines running for years, even decades. The result is a propulsion system that's both powerful and incredibly efficient, capable of sustaining long-duration missions without the need for massive fuel tanks. The advantages of this technology are hard to overstate. Traditional chemical rockets are limited by the amount of fuel they can carry, but nuclear electric propulsion sidesteps this issue entirely. By using a nuclear reactor to generate electricity, spacecraft can carry far less propellant, freeing up valuable space for scientific instruments, life support systems, or even larger crews. This makes it an ideal choice for missions to distant destinations like Jupiter, Saturn, or even the icy worlds of the Kuiper Belt, where efficiency and endurance are critical. But the benefits don't stop there. Nuclear electric propulsion also offers incredible flexibility. Unlike systems that rely on a single type of propulsion, this hybrid approach allows spacecraft to operate at different thrust levels depending on the mission's needs. Need to make a quick course correction, crank up the power, traveling through the vast emptiness of deep space, dial it back to conserve energy. It's this adaptability that makes nuclear electric propulsion such a promising solution for the challenges of long-duration space travel. Of course, no technology is without its hurdles. Designing a nuclear reactor that's both compact and reliable enough for space travel is no small feat. There's also the challenge of managing heat, as nuclear reactors generate a significant amount of it, and keeping the system cool in the vacuum of space is a complex engineering problem. And let's not forget the public's perception of nuclear technology, which often comes with concerns about safety and environmental impact. These challenges are real, but they're not insurmountable. Advances in reactor design, materials, science, and safety protocols are steadily making nuclear electric propulsion a more viable option. The potential applications of this technology are nothing short of transformative. Imagine sending a probe to Europa, Jupiter's icy moon, to search for signs of life beneath its frozen surface, or consider a mission to Pluto, where a spacecraft could spend years studying the dwarf planet and its moons in unprecedented detail. With nuclear electric propulsion, these missions become not just possible, but practical. It's a technology that could open up the outer solar system in ways we've only dreamed of, bringing distant worlds within our reach. What makes nuclear electric propulsion so exciting is its ability to bridge the gap between the familiar and the futuristic. It takes the proven efficiency of ion, drives and combines it with the raw power of nuclear energy, creating a system that's greater than the sum of its parts. And as we continue to push the boundaries of space exploration, it's innovations like these that will help us go farther, faster, and more sustainably than ever before. This isn't just about building better engines, it's about redefining what's possible in the vast expanse of space. What if we could tap into the same power source that fuels the sun itself? Fusion propulsion takes us into the realm of the extraordinary, offering a glimpse of a future where spacecraft are powered by the very processes that light up the cosmos. This isn't just another step forward in propulsion technology. It's a leap into a new era of space travel, one where the stars might no longer be out of reach. At its core, fusion propulsion relies on the same principle that powers stars, combining light atomic nuclei like hydrogen to form heavier elements, releasing colossal amounts of energy in the process. Unlike fission, which splits atoms apart, fusion binds them together, creating a reaction that's both cleaner and far more energetic. The result, a propulsion system capable of delivering speeds and efficiency that dwarf anything we've achieved so far. The promise of fusion propulsion is nothing short of revolutionary. Imagine spacecraft traveling at a fraction of the speed of light, cutting the journey to Alpha Centauri, our nearest star system, from tens of thousands of years to just a few decades. For interstellar missions, this could be the game changer we've been waiting for. But even closer to home, fusion propulsion could transform how we explore our own solar system, slashing travel times to Mars and beyond while opening up new possibilities for crewed missions to the outer planets. Yet, as tantalizing as this technology is, it's not without its challenges. Achieving controlled fusion here on Earth has proven to be one of the most difficult scientific and engineering feats in history. The conditions required to sustain a fusion reaction, extreme temperatures and pressures, are incredibly demanding. In space, these challenges are amplified. Engineers must figure out how to create and maintain these conditions in a compact, lightweight system that can withstand the rigors of space travel. And then there's the issue of fuel. While hydrogen is abundant, sourcing and storing it in a form suitable for fusion is no small task. Despite these hurdles, progress is being made. Experimental reactors like ITER, the International Fusion Project, are paving the way for breakthroughs in controlled fusion. While these reactors are designed for energy production on Earth, the principles they're proving could one day be adapted for space-based fusion propulsion. And then, there are concepts like the direct fusion drive, a compact fusion engine being developed specifically for spacecraft, which could bring this technology closer to reality. The potential applications are staggering. Fusion propulsion could enable missions to the outer solar system in months rather than years, making it feasible to explore the icy moons of Jupiter and Saturn, or even send probes to the Kuiper belt. And for interstellar travel, it could be the key to reaching nearby star systems within a human lifetime. It's a vision that transforms space exploration from a series of isolated missions into a continuous journey of discovery. But fusion propulsion isn't just about speed or distance, it's about redefining what's possible. It's a technology that challenges us to think bigger, to imagine a future where the vast distances of space are no longer a barrier. It's a reminder that the stars aren't just points of light in the sky, they're destinations waiting to be reached. And with fusion propulsion, that future might be closer than we think. As we continue to push the boundaries of science and engineering, fusion propulsion stands as a beacon of what's possible when we dare to dream big. It's a technology that holds the promise of not just reaching the stars, but of bringing them within our grasp. And in doing so, it invites us to imagine a universe where humanity's journey is no longer confined to the limits of our own solar system, but extends to the far reaches of the galaxy and beyond. What if the key to unlocking the stars lies in a substance so rare and powerful that it defies our understanding of physics? Enter antimatter, the ultimate energy source and perhaps the most tantalizing prospect for future space propulsion. When antimatter meets matter, the result is a colossal release of energy, more efficient than anything we've ever harnessed. This isn't just science fiction, it's a concept grounded in real physics, one that could revolutionize how we think about speed, distance, and the very nature of space travel. At its core, antimatter is the mirror image of ordinary matter. For every particle of matter, like protons, electrons, and neutrons, there's a corresponding antiparticle with the opposite charge. When these two collide, they annihilate each other, converting their entire mass into energy. This process, governed by Einstein's famous equation E=mc², is staggeringly efficient. In fact, it's the most efficient energy conversion known to science, releasing energy with 100% efficiency. To put that into perspective, just 1 gram of antimatter could produce an explosion equivalent to tens of thousands of tons of TNT. Now, imagine harnessing that power not for destruction, but for propulsion. The potential of antimatter propulsion is mind-boggling. A spacecraft powered by this technology could theoretically reach relativistic speeds close to that of light, making interstellar travel not just a dream, but a realistic possibility. Imagine cutting the journey to Alpha Centauri, our nearest star system, from tens of thousands of years to just a few decades. For the first time in history, we could send probes, or even crewed missions, to explore other star systems within a human lifetime. It's a vision that redefines what's possible in space exploration, but as exciting as this technology sounds, it's not without its challenges. Producing antimatter is incredibly difficult and expensive. Current methods, like those used at CERN Large Hadron Collider, generate only tiny amounts, mere nanograms, at a cost of billions of dollars. Scaling up production to the quantities needed for space travel would require breakthroughs in both technology and cost efficiency. And then there's the issue of storage. Antimatter can't simply be stored in a conventional fuel tank. It requires incredibly precise magnetic fields to prevent it from coming into contact with matter and annihilating prematurely. Even a single misstep could result in catastrophic energy release, making safe storage one of the most significant engineering challenges of our time. Despite these hurdles, scientists and engineers are making progress. Concepts like antimatter rockets, which use the energy from matter-antimatter annihilation to heat a propellant, are being actively studied. There's also the idea of using antimatter as a catalyst for fusion reactions, combining its immense energy with the more accessible technology of fusion propulsion. These hybrid approaches could make antimatter propulsion more practical, at least in the near term. The implications of this technology extend far beyond speed. Antimatter propulsion could enable missions to the outer reaches of our solar system in weeks rather than years, opening up new possibilities for exploring distant worlds like Pluto or the Kuiper Belt. It could also provide a sustainable way to travel to and from Mars, making crewed missions more feasible and less risky. And in the long term, it could be the key to unlocking the stars, transforming humanity into a truly interstellar species. What makes antimatter propulsion so compelling is its sheer potential. It's a technology that challenges us to think beyond the limits of current science and engineering, to imagine a future where the vast distances of space are no longer a barrier. It's a reminder that the universe is full of possibilities, waiting for us to discover and harness them. And while the road to antimatter propulsion is long and fraught with challenges, the rewards reaching the stars, exploring new worlds, and expanding the horizons of human knowledge are worth every effort. As we look to the future, antimatter stands as a symbol of humanity's relentless drive to explore and innovate. It's a technology that pushes the boundaries of what we thought was possible, inviting us to dream bigger and reach further. And in doing so, it reminds us that the cosmos is not just a place to visit. It's a frontier to conquer, one groundbreaking discovery at a time. Now, let's turn our attention to a propulsion method that's as elegant as it is ingenious: solar sails. Imagine a spacecraft that doesn't rely on fuel, engines, or even nuclear reactions, but instead harnesses the gentle push of sunlight itself. It's a concept that feels almost poetic, a cosmic dance between a spacecraft and the photons streaming from the sun. And while it might sound like something out of a dream, solar sails are very real, with missions like LightSail 2 already proving their potential. So, how does it work? At its heart, a solar sail is a massive, ultra-thin reflective sheet. Think of it as a giant mirror in space. When sunlight strikes this mirror, the photons exert a tiny but constant pressure, pushing the sail, and the spacecraft attached to it forward. It's a bit like a boat catching the wind, except here, the wind is made of light. Over time, this gentle push builds up, allowing the spacecraft to reach incredible speeds without ever needing to carry or burn fuel. The beauty of solar sails lies in their simplicity and sustainability. Unlike traditional propulsion systems, which require fuel that can run out, solar sails have an almost limitless source of energy: sunlight. This makes them ideal for long-duration missions where efficiency and endurance are key. Imagine a probe traveling to the outer reaches of the solar system, propelled not by bulky engines or finite fuel reserves, but by the steady, unending light of the sun. It's a vision that's not only practical but profoundly elegant. One of the most exciting applications of solar sails is their potential for interstellar travel. While they might not be the fastest option for getting to nearby stars, their ability to operate indefinitely makes them a strong candidate for sending probes to distant star systems. Once a solar sail spacecraft reaches a high enough speed, it could continue accelerating for years, even decades, building up enough velocity to cross the vast distances between stars. It's a slow but steady approach, one that could eventually carry humanity's curiosity to the farthest reaches of the galaxy. Of course, solar sails aren't without their challenges. The thrust they generate is incredibly small, which means they're not well suited for missions that require quick acceleration or precise maneuvering. And while sunlight is abundant within our solar system, its intensity drops off dramatically as you move farther from the sun. To overcome this, future solar sails might rely on powerful lasers to provide an extra boost, pushing the spacecraft to even greater speeds. It's a concept known as laser propulsion, and it could take solar sails from a niche technology to a cornerstone of interstellar exploration. What makes solar sails so compelling is their ability to turn a simple idea into something truly transformative. They remind us that sometimes the most revolutionary technologies are the ones that embrace simplicity rather than complexity. By harnessing the power of sunlight, solar sails offer a sustainable, fuel-free way to explore the cosmos, opening up new possibilities for missions that were once thought impossible. As we look to the future, solar sails stand as a testament to human creativity and our ability to find solutions in the most unexpected places. They invite us to rethink how we approach space travel, not by building bigger engines or carrying more fuel, but by working in harmony with the natural forces of the universe. And in doing so, they offer a glimpse of a future where the stars are no longer out of reach, but a destination we can sail toward, one photon at a time. Now, let's explore a propulsion concept that feels like it's straight out of a sci-fi blockbuster: laser propulsion. Imagine a spacecraft being propelled not by rockets or sails, but by beams of light fired from Earth. It's a futuristic idea that's as bold as it is brilliant, and it could hold the key to reaching nearby star systems within a human lifetime. This isn't just about speed, it's about redefining how we think about energy, distance, and the very mechanics of space travel. So, how does laser propulsion work? Picture this: a ground-based laser array, possibly spanning kilometers, firing an intense beam of light at a spacecraft equipped with a reflective sail. As the photons from the laser strike the sail, they transfer momentum, pushing the spacecraft forward. Unlike traditional propulsion systems, which rely on carrying fuel or reacting to external forces, laser propulsion uses energy beamed from Earth, eliminating the need for heavy fuel tanks and allowing the spacecraft to travel lighter and faster. It's like having a cosmic slingshot, where the laser is the sling and the spacecraft is the projectile, hurtling through space at speeds that could reach a significant fraction of the speed of light. The implications for interstellar travel are staggering. With laser propulsion, a mission to Alpha Centauri, our nearest star system, could take just a few decades instead of tens of thousands of years. That's the kind of breakthrough that could make interstellar exploration a reality within our lifetime. But the potential doesn't stop there. Laser propulsion could also revolutionize travel within our solar system, enabling missions to Mars, Jupiter, or even Pluto in weeks or months rather than years. It's a technology that could shrink the vast distances of space, bringing distant worlds within our reach. Of course, there are challenges to overcome. Building a laser array powerful enough to propel a spacecraft to interstellar speeds is no small feat. The laser would need to be incredibly precise, focusing its beam over distances of millions or even billions of kilometers. Then there's the issue of power. Such a laser would require immense amounts of energy, potentially rivaling the output of entire nations. And let's not forget the spacecraft itself. Designing a sail that can withstand the intense heat and pressure of a laser beam while remaining lightweight and durable is a significant engineering hurdle. But the rewards could be worth the effort. Laser propulsion offers a way to explore the cosmos without the limitations of traditional propulsion systems. It's a technology that could make interstellar travel not just possible, but practical, opening up new frontiers for humanity to explore. And as we continue to push the boundaries of science and engineering, laser propulsion stands as a testament to our ability to dream big and turn those dreams into reality. What makes this concept so exciting is its potential to transform how we think about space travel. It's not just about building faster rockets or more efficient engines. It's about reimagining the very foundations of propulsion. By harnessing the power of light, we could unlock a future where the stars are no longer distant points of light, but destinations waiting to be explored. It's a vision that challenges us to think beyond the limits of current technology and embrace the possibilities of what could be. As we look to the future, laser propulsion offers a glimpse of a world where the vast distances of space are no longer a barrier. It's a technology that invites us to dream of a universe where humanity's journey extends far beyond the confines of our solar system, reaching out to the stars and beyond. And in doing so, it reminds us that the cosmos is not just a place to visit, it's a frontier to explore, one beam of light at a time. Now, let's venture into a propulsion concept that turns the very fabric of space into a source of power: magnetic sails. Imagine a spacecraft that doesn't rely on engines, fuel, or even sunlight, but instead uses the invisible forces of magnetism to glide through the cosmos. It's a concept that feels almost magical, a cosmic sailboat catching the wind of the universe itself. But this isn't fantasy, it's a scientifically grounded idea that could reshape how we think about interstellar travel. At the heart of a magnetic sail lies a simple yet ingenious principle: the solar wind. Streaming from the sun at speeds of up to several hundred kilometers per second, this flow of charged particles, mostly protons and electrons, creates a constant, invisible breeze throughout our solar system. A magnetic sail works by deploying a large magnetic field, often generated by superconducting coils, to deflect these charged particles. As the particles interact with the magnetic field, they transfer momentum to the spacecraft, gently pushing it forward. It's like a sailboat catching the wind, except the wind is made of charged particles, and the sail is a magnetic field. The beauty of magnetic sails lies in their efficiency and sustainability. Unlike traditional propulsion systems, which require fuel that can run out, magnetic sails tap into an endless source of energy, the solar wind. This makes them ideal for long-duration missions, where carrying fuel is a major limitation. Imagine a spacecraft traveling to the outer reaches of the solar system, propelled not by bulky engines or finite fuel reserves, but by the steady, unending flow of particles streaming from the sun. It's a vision that's as practical as it is elegant. One of the most exciting applications of magnetic sails is their potential for interstellar travel. While they might not be the fastest option for reaching nearby stars, their ability to operate indefinitely makes them a strong candidate for sending probes to distant star systems. Once a magnetic sail spacecraft reaches a high enough speed, it could continue accelerating for years, even decades, building up enough velocity to cross the vast distances between stars. It's a slow but steady approach, one that could eventually carry humanity's curiosity to the farthest reaches of the galaxy. But magnetic sails aren't just about endurance, they're also about precision. Because they rely on the solar wind, their performance can be optimized by adjusting the strength and orientation of the magnetic field. This allows spacecraft to maneuver with incredible accuracy, making them invaluable for missions that require delicate adjustments, like orbiting distant celestial bodies or maintaining position in deep space. It's a level of control that traditional propulsion systems simply can't match. Of course, no technology is without its challenges. Scaling up magnetic sails for interstellar travel is no small feat. The magnetic fields required to deflect particles at such vast distances would need to be immense, and generating them would require advanced superconducting materials and power systems. Then there's the issue of the solar wind itself. Its intensity drops off dramatically as you move farther from the sun, which means magnetic sails would need to rely on other sources of charged particles, like interstellar plasma, to maintain thrust. These are significant hurdles, but they're not insurmountable. Advances in materials, science, and energy generation are steadily making magnetic sails a more viable option. What makes this concept so compelling is its ability to turn the cosmos itself into a source of propulsion. It's a reminder that the universe is full of untapped resources, waiting for us to discover and harness them. By using magnetic sails, we're not just building better engines, we're learning to work with the natural forces of space, turning the solar wind into a cosmic highway that could carry us to the stars. As we look to the future, magnetic sails stand as a testament to human ingenuity and our ability to find solutions in the most unexpected places. They invite us to rethink how we approach space travel, not by carrying more fuel or building bigger engines, but by tapping into the energy that's already flowing through the cosmos. And in doing so, they offer a glimpse of a future where the stars are no longer out of reach, but a destination we can sail toward, one particle at a time. What if the fuel for interstellar travel wasn't something we had to carry with us, but something we could scoop up along the way? Enter fusion-driven ramjets, a concept so bold it feels like it's straight out of a visionary's dream. These futuristic engines, also known as bussard ramjets, don't rely on traditional fuel tanks or even preloaded propellant. Instead, they collect hydrogen from the vast expanse of interstellar space itself, using it to power fusion reactions that propel the spacecraft forward. It's a concept that turns the emptiness of space into a cosmic gas station, offering a potentially limitless source of energy for our journey to the stars. At the heart of this idea is a simple yet profound principle. The universe is filled with hydrogen, the most abundant element in existence. In the thin but ever-present gas that permeates interstellar space, hydrogen atoms float freely, waiting to be harnessed. A fusion-driven ramjet would deploy a massive electromagnetic field, often described as a ram scoop, to collect these atoms as the spacecraft travels at incredible speeds. Once captured, the hydrogen would be funneled into a fusion reactor, where it's heated to extreme temperatures and pressures, triggering a fusion reaction that releases immense energy. This energy is then used to generate thrust, propelling the spacecraft even faster, and enabling it to collect even more hydrogen as it goes. It's a self-sustaining cycle, one that could theoretically allow a spacecraft to travel indefinitely without ever running out of fuel. The elegance of this concept is hard to overstate. By tapping into the natural resources of space itself, fusion-driven ramjets could eliminate one of the biggest hurdles of interstellar travel, the need to carry massive amounts of fuel. Traditional propulsion systems are limited by the tyranny of the rocket equation, which states that the more fuel you carry, the more fuel you need just to move that fuel. But with a ramjet, the fuel is all around you, scattered across the cosmos like cosmic breadcrumbs. It's a solution that's as resourceful as it is revolutionary, turning the vast emptiness of space into an advantage rather than a limitation. Of course, the challenges of building such a system are immense. Collecting enough hydrogen from the sparse interstellar medium would require a ram scoop of staggering size, potentially spanning hundreds or even thousands of kilometers. Generating and maintaining the electromagnetic fields needed to gather and compress the hydrogen is another monumental task, requiring advances in materials science and energy generation that we're only beginning to explore. And then there's the fusion reactor itself, which would need to be compact, efficient, and capable of operating reliably in the harsh conditions of deep space. These are not small hurdles, but they're not insurmountable either. As our understanding of fusion technology and electromagnetic systems continues to grow, the dream of a bussard ramjet becomes increasingly plausible. What makes this concept so compelling is its potential to transform interstellar travel from a one-way journey into a sustainable, continuous exploration. A spacecraft powered by a fusion-driven ramjet wouldn't just reach the stars. It could keep going, propelled by the very fabric of the universe itself. Imagine a future where humanity's reach extends far beyond our solar system, where the stars are no longer distant points of light, but stepping stones on an endless journey of discovery. It's a vision that redefines what's possible, turning the cosmos into a place of boundless opportunity. But fusion-driven ramjets aren't just about speed or distance, they're about reimagining our relationship with space. They challenge us to think beyond the limits of current technology and to see the universe not as a barren void, but as a resource-rich environment waiting to be explored. It's a reminder that the solutions to some of our greatest challenges might already be out there, floating in the interstellar medium, just waiting for us to reach out and grab them. As we look to the future, fusion-driven ramjets stand as a testament to human ingenuity and our unyielding desire to explore the unknown. They invite us to dream of a cosmos where the journey is as important as the destination, where the stars are not just places to visit, but pathways to a future we've only begun to imagine. And in doing so, they remind us that the universe is not just a place to explore, it's a partner in our journey, offering the fuel we need to reach the stars. What if the vast distances of space could be folded, allowing us to travel faster than light without breaking the laws of physics? Enter warp drives, a concept that feels like it's straight out of science fiction, but one that scientists are now taking seriously. Unlike traditional propulsion methods, which push spacecraft through space, warp drives work by bending space-time itself, creating a warp bubble that moves the ship through the cosmos. It's a mind-bending idea, but recent theoretical advances suggest it might not be as far-fetched as it sounds. At the heart of this concept lies Albert Einstein's theory of general relativity, which tells us that space-time isn't rigid. It can be warped, stretched, and folded. A warp drive would exploit this by compressing space in front of the spacecraft and expanding it behind, effectively creating a shortcut through the fabric of the universe. The ship itself wouldn't move through space. Instead, space would move around the ship, allowing it to travel faster than light without technically violating the cosmic speed limit. It's like standing on a moving walkway at the airport. You're not walking faster, but the ground beneath you is, so you reach your destination more quickly. The potential of warp drives is staggering. Imagine traveling to Alpha Centauri, our nearest star system, in just a matter of weeks instead of tens of thousands of years. It's the kind of breakthrough that could make interstellar exploration not just possible, but practical. And it's not just about speed. Warp drives could also open up entirely new possibilities for exploration, allowing us to reach distant galaxies and uncover the mysteries of the universe in ways we've only dreamed of. But as exciting as this technology sounds, it's not without its challenges. One of the biggest hurdles is energy. Creating a warp bubble requires an immense amount of energy, far more than we're currently capable of generating. Some theoretical models suggest that exotic matter with negative energy density might be needed to stabilize the bubble, but such materials have yet to be discovered. There's also the issue of controlling the warp field. If not managed carefully, a warp bubble could collapse, releasing catastrophic amounts of energy that could destroy the spacecraft and anything nearby. These are significant obstacles, but they are not insurmountable. Advances in physics and engineering are steadily bringing us closer to understanding how warp drives might work, and some researchers are even exploring ways to reduce the energy requirements to more practical levels. What makes warp drives so compelling is their ability to challenge our understanding of the universe. They're not just a new kind of engine, they're a new way of thinking about space and time. By bending the very fabric of reality, warp drives invite us to imagine a future where the vast distances of space are no longer a barrier, but a pathway to discovery. It's a vision that pushes the boundaries of what we thought was possible, reminding us that the universe is full of surprises waiting to be uncovered. As we look to the future, warp drives stand as a symbol of humanity's relentless curiosity and our desire to explore the unknown. They're a reminder that the final frontier might not be as distant as it seems, and that the stars are waiting for us to reach out and touch them. And while the road to warp travel is long and filled with challenges, the rewards unlocking the secrets of the cosmos and expanding the horizons of human knowledge are worth every effort. The journey to the stars may begin not with a roar of engines, but with a whisper of space-time itself. Now, let's dive into one of the most fascinating and mind-bending concepts in propulsion technology, the Alcubierre drive. Named after physicist Miguel Alcubierre, who first proposed the idea in the 1990s, this theoretical concept takes the idea of warp drives to a whole new level. Instead of pushing a spacecraft through space, the Alcubierre drive would manipulate the fabric of space-time itself, creating a warp bubble that moves the ship through the cosmos. It's a concept that feels like it belongs in a science fiction novel, but it's grounded in real physics, specifically Einstein's theory of general relativity. Here's how it works. The Alcubierre drive would contract space-time in front of the spacecraft while expanding it behind, effectively creating a wave that carries the ship along. The spacecraft itself wouldn't move through space in the traditional sense. Instead, it would ride this wave like a surfer gliding on the ocean. This means the ship could theoretically travel faster than the speed of light without violating the laws of physics, because it's not actually moving through space. It's space itself that's moving around it. It's a subtle but profound distinction, one that opens up the possibility of interstellar travel on a scale we've only dreamed of. The implications of this technology are staggering. Imagine a future where a journey to Alpha Centauri, our nearest star system, takes weeks instead of tens of thousands of years. This isn't just about speed, it's about redefining what's possible in space exploration. The Alcubierre drive could make interstellar travel not just feasible, but practical, opening up the entire galaxy to exploration and discovery. It's a vision that transforms the cosmos from a distant, unreachable frontier into a place we can visit and study in detail. But as groundbreaking as this concept is, it's not without its challenges. One of the biggest hurdles is energy. Creating a warp bubble requires an unimaginable amount of energy, far more than we're currently capable of generating. Some estimates suggest that it would take the equivalent of the entire energy output of a star to power an Alcubierre drive, and then there's the issue of exotic matter. To stabilize the warp bubble, we'd need a type of matter with negative energy density, something that has never been observed in nature. These are significant obstacles, but they're not insurmountable. Advances in physics and engineering are steadily bringing us closer to understanding how these challenges might be overcome. What makes the Alcubierre drive so compelling is its ability to challenge our understanding of the universe. It's not just a new kind of engine, it's a new way of thinking about space and time. By bending the very fabric of reality, the Alcubierre drive invites us to imagine a future where the vast distances of space are no longer a barrier, but a pathway to discovery. It's a vision that pushes the boundaries of what we thought was possible, reminding us that the universe is full of surprises waiting to be uncovered. While the Alcubierre drive remains a theoretical concept for now, it's a powerful reminder of the incredible potential of human ingenuity. It shows us that the solutions to some of our greatest challenges might lie not in building bigger or faster engines, but in reimagining the very nature of space and time. And as we continue to explore the mysteries of the cosmos, the dream of bending space-time remains alive and well, inviting us to imagine a future where the stars are no longer out of reach, but a destination we can visit, one warp bubble at a time. Now, let's step into one of the most intriguing and controversial corners of propulsion technology, quantum vacuum thrusters, often referred to as EM drives. Imagine a spacecraft that doesn't need fuel, doesn't expel exhaust, and somehow generates thrust by interacting with the very fabric of the universe itself. It sounds like magic, but it's a concept that's been tested in labs, and it's sparked heated debates among scientists and engineers around the world. At its core, the idea behind quantum vacuum thrusters is as bold as it is baffling. These devices claim to create thrust by bouncing microwaves around a specially shaped chamber, producing a tiny but measurable force. The twist: there's no propellant involved, no burning fuel, no expelled ions, nothing. Instead, the thrust is said to come from the quantum vacuum, a sea of virtual particles that constantly pop in and out of existence according to the strange rules of quantum mechanics. It's like pushing against the very fabric of reality itself, and if it works, it could revolutionize how we think about space travel. The potential applications of this technology are staggering. Without the need for fuel, spacecraft could become lighter, cheaper, and capable of traveling farther than ever before. Missions to Mars or the outer planets could become routine, and interstellar travel, once the stuff of science fiction, might suddenly seem within reach. Imagine sending a probe to Alpha Centauri without worrying about fuel constraints, or designing deep space habitats that can sustain thrust for decades. The possibilities are as vast as the cosmos itself, but here's the catch: quantum vacuum thrusters defy some of the most fundamental laws of physics, particularly Newton's third law, which states that every action has an equal and opposite reaction. Without expelling mass, how can a spacecraft generate thrust? It's a question that's left even the most brilliant minds scratching their heads. Some researchers argue that the thrust observed in experiments might be the result of experimental error or unaccounted for forces, while others believe it could be evidence of new physics waiting to be discovered. The debate over quantum vacuum thrusters has been fierce, with skeptics and supporters clashing over the validity of the results. On one side, there's excitement about the potential for a propulsion system that could rewrite the rules of space travel. On the other, there's caution, as many scientists insist that extraordinary claims require extraordinary evidence, and so far, that evidence has been elusive. Repeated experiments have produced mixed results, with some showing small but measurable thrust and others finding nothing at all. It's a scientific mystery that's far from being solved. What makes this concept so captivating is its audacity. Quantum vacuum thrusters challenge our understanding of the universe, forcing us to question what we think we know about physics, energy, and motion. They remind us that sometimes the most revolutionary ideas are the hardest to prove, and that the path to discovery is often paved with skepticism, debate, and a willingness to explore the unknown. As we look to the future, quantum vacuum thrusters stand as a symbol of humanity's relentless curiosity and our drive to push the boundaries of what's possible. They invite us to imagine a world where the rules of space travel are rewritten, where the cosmos is no longer bound by the limitations of fuel or propulsion. And while the road to understanding these devices is long and uncertain, the journey itself is a testament to the power of human ingenuity and our unyielding desire to explore the mysteries of the universe. Whether quantum vacuum thrusters ultimately prove to be a groundbreaking breakthrough or a fascinating dead end, they remind us that science is a process of questioning, testing, and reimagining. And in that process, we often find the most extraordinary possibilities, not just in the answers we discover, but in the questions we dare to ask. Now, let's explore a propulsion concept that feels almost poetic in its simplicity: photonic propulsion. Imagine harnessing the power of light itself to push a spacecraft through the void of space. It's a technology that doesn't rely on fuel, engines, or even traditional propellants. Instead, it taps into the momentum of photons, the tiny packets of energy that make up light. This isn't just a theoretical idea, it's a concept that's already being tested, and it could hold the key to reaching incredible speeds in the cosmos. At its core, photonic propulsion works by using the momentum of photons to generate thrust. When light strikes a surface, it exerts a tiny but measurable force, a phenomenon known as radiation pressure. While this force is minuscule, it's constant, and over time, it can build up to significant speeds. Photonic propulsion takes this principle and scales it up, using powerful lasers to direct intense beams of light at a reflective sail attached to a spacecraft. As the photons from the laser strike the sail, they transfer their momentum, gently pushing the spacecraft forward. It's like sailing on a cosmic breeze, except the wind is made of light. The potential of this technology is breathtaking. Unlike traditional propulsion systems, which are limited by the amount of fuel they can carry, photonic propulsion offers a way to achieve incredibly high speeds without the need for bulky fuel tanks. This makes it an ideal candidate for interstellar travel, where efficiency and endurance are critical. Imagine a spacecraft traveling at a significant fraction of the speed of light, propelled not by burning chemicals or nuclear reactions, but by the steady push of photons. It's a vision that could transform how we explore the universe, making distant star systems reachable within a human lifetime. But photonic propulsion isn't just about speed, it's also about precision. Because the thrust is generated by light, it can be finely controlled, allowing spacecraft to maneuver with incredible accuracy. This makes it invaluable for missions that require delicate adjustments, like orbiting distant celestial bodies or maintaining position in deep space. And since the energy source, light, is beamed from Earth or a space-based laser array, the spacecraft itself can be lightweight and compact, freeing up space for scientific instruments or life support systems. Of course, there are challenges to overcome. Scaling up photonic propulsion to achieve interstellar speeds requires immense amounts of energy. The laser arrays needed to power such missions would need to be incredibly powerful, potentially rivaling the energy output of entire nations. Then there's the issue of targeting. Focusing a laser beam over distances of millions or even billions of kilometers is no small feat. And let's not forget the spacecraft itself, which would need a sail large enough to capture the laser's energy while remaining lightweight and durable enough to withstand the rigors of space travel. Despite these hurdles, the potential rewards are too great to ignore. Photonic propulsion represents a paradigm shift in how we think about space travel, offering a way to explore the cosmos without the limitations of traditional propulsion systems. It's a reminder that sometimes the most revolutionary technologies are the ones that embrace simplicity and elegance, turning the fundamental forces of the universe into tools for exploration. What makes photonic propulsion so compelling is its ability to challenge our assumptions about what's possible. It invites us to imagine a future where the vast distances of space are no longer a barrier, but a highway paved with light. And as we continue to push the boundaries of science and engineering, this technology stands as a testament to humanity's ingenuity and our unyielding desire to explore the unknown. The power of light could take us to new worlds, not just as distant dreams, but as destinations waiting to be reached. Now, let's imagine a future where spacecraft don't need to carry their own fuel at all. Instead, they're powered by beams of energy sent from Earth or even orbiting stations. This is the promise of beamed energy propulsion, a concept that could revolutionize how we think about space travel. By transmitting energy remotely, we could eliminate the need for heavy fuel tanks, freeing up spacecraft to travel farther, faster, and more efficiently than ever before. At its core, beamed energy propulsion works by sending concentrated energy, often in the form of lasers or microwaves, to a spacecraft equipped with a receiver. This receiver converts the incoming energy into thrust, propelling the spacecraft forward. Think of it like a cosmic version of wireless charging, except instead of powering your phone, we're powering a ship bound for the stars. The beauty of this system is that the energy source stays behind, whether it's on Earth or in orbit, while the spacecraft itself can travel lighter and faster without the burden of carrying fuel. One of the most exciting advantages of this technology is its scalability. Unlike traditional propulsion systems, which are limited by the amount of fuel they can carry, beamed energy propulsion offers a nearly limitless source of power. This makes it ideal for long-duration missions where efficiency and endurance are critical. Imagine a probe traveling to the outer reaches of the solar system, powered not by finite fuel reserves, but by a steady stream of energy beamed from a ground-based laser array. It's a vision that could make deep space exploration more sustainable and far-reaching than ever before. But the potential doesn't stop there. Beamed energy propulsion could also dramatically reduce travel times within our solar system. By providing a continuous source of energy, spacecraft could maintain high speeds for longer periods, cutting the journey to Mars or even Jupiter from months to weeks. For crewed missions, this could mean less time exposed to the hazards of deep space and more time conducting groundbreaking research at the destination. It's a game changer for both robotic and human exploration, offering a way to shrink the vast distances of space. Of course, there are challenges to overcome. Building the infrastructure for beamed energy propulsion is no small task. Ground-based laser arrays would need to be incredibly powerful and precise, capable of focusing their beams over millions of kilometers. Space-based systems, while potentially more flexible, would require significant advancements in orbital construction and maintenance. And then there's the issue of efficiency, ensuring that the energy transmitted is effectively converted into thrust without significant losses along the way. These are significant hurdles, but they're not insurmountable, especially as our technology continues to evolve. What makes beamed energy propulsion so compelling is its ability to transform the way we approach space travel. It's not just about building better engines, it's about rethinking the very concept of propulsion. By decoupling the energy source from the spacecraft, we're opening up new possibilities for exploration, from missions to the outer planets to interstellar probes that could one day reach nearby star systems. It's a vision that challenges us to think beyond the limits of current technology and embrace the potential of what's possible. As we look to the future, beamed energy propulsion stands as a testament to human ingenuity and our ability to find solutions in the most unexpected places. It's a reminder that the universe is full of untapped resources, waiting for us to discover and harness them, and in doing so, it invites us to imagine a future where the stars are no longer out of reach, but destinations we can power toward, one beam of energy at a time. Imagine a propulsion system that doesn't need fuel, engines, or even sunlight, just a long, conductive wire and the magnetic field of our own planet. This is the fascinating concept behind electrodynamic tethers, a technology that turns Earth's magnetic field into a source of thrust. It's a clever, almost elegant way to move through space, and it's already being tested in orbit. By harnessing the natural forces of our planet, electrodynamic tethers could offer a sustainable, fuel-free way to keep satellites in orbit or even propel spacecraft to new destinations. So, how does it work? At its core, an electrodynamic tether is a long, thin wire made of conductive material, often several kilometers in length. When deployed in orbit, this wire interacts with Earth's magnetic field, generating an electric current as it moves through the field lines. This current, in turn, creates its own magnetic field, which interacts with Earth's field to produce a force, essentially thrust. It's like a cosmic version of a sailboat catching the wind, except the wind is the planet's magnetic force, and the sail is a simple wire. The result is a propulsion system that's both lightweight and incredibly efficient, with no need for fuel or complex engines. One of the most exciting applications of electrodynamic tethers is their potential to extend the lifespan of satellites. In low Earth orbit, satellites face constant drag from the thin upper atmosphere, which gradually slows them down and causes their orbits to decay. By using an electrodynamic tether, a satellite could generate thrust to counteract this drag, effectively keeping itself in orbit without the need for fuel. This could drastically reduce the cost of maintaining satellites and even prevent them from becoming space debris. It's a win-win for both space agencies and the environment. But the possibilities don't stop there. Electrodynamic tethers could also be used to propel spacecraft on longer missions. By generating continuous thrust over time, they could enable missions to higher orbits or even to other planets, all without the need for heavy fuel tanks. Imagine a future where spacecraft are powered not by chemical reactions or nuclear energy, but by the magnetic field of Earth itself. It's a vision that's as innovative as it is inspiring, offering a new way to explore the cosmos. Of course, no technology is without its challenges. One of the biggest hurdles for electrodynamic tethers is their reliance on Earth's magnetic field, which limits their use to orbits where the field is strong enough to generate meaningful thrust. This means they're not well suited for deep space missions or destinations beyond the influence of Earth's magnetic field. There's also the issue of tether durability. These wires must withstand the harsh conditions of space, including micrometeoroids and radiation, without breaking or degrading over time. And then, there's the challenge of deployment. Unfurling and maintaining a kilometers-long wire in the vacuum of space is no small feat. Despite these challenges, electrodynamic tethers represent a promising step toward more sustainable space travel. They remind us that sometimes the most revolutionary technologies are the ones that work in harmony with the natural forces around us. By tapping into Earth's magnetic field, we're not just building better engines, we're learning to use the resources already available to us in new and ingenious ways. What makes this technology so compelling is its simplicity and elegance. It's a reminder that the solutions to some of our greatest challenges might be hiding in plain sight, waiting for us to see them in a new light. As we continue to explore the possibilities of electrodynamic tethers, we're not just reimagining propulsion, we're redefining our relationship with the planet that makes it all possible. The Earth itself could be the key to powering our journey to the stars, one tether at a time. Now, let's turn our attention to a propulsion system that harnesses the most abundant source of energy in our solar system, the Sun itself. Solar thermal propulsion takes the familiar concept of sunlight and transforms it into a powerful tool for space travel. By using mirrors to focus the sun's rays, this technology heats a propellant to extreme temperatures, generating thrust without the need for heavy fuel tanks or complex engines. It's a brilliant marriage of simplicity and innovation, one that could make interplanetary travel more sustainable and efficient than ever before. At its core, solar thermal propulsion works by concentrating sunlight onto a heat exchanger, which then heats a propellant, often hydrogen or another lightweight gas, to incredibly high temperatures. As the propellant heats up, it expands and is expelled through a nozzle, creating thrust. Think of it as a cosmic version of a magnifying glass focusing sunlight to start a fire, except here, the fire is a controlled, powerful force propelling a spacecraft through the void. The beauty of this system is its reliance on the sun's energy, an inexhaustible resource that's freely available throughout the solar system. One of the most compelling advantages of solar thermal propulsion is its efficiency. Unlike chemical rockets, which burn fuel in explosive bursts, this system offers a steady, continuous source of thrust. This makes it ideal for missions that require endurance, such as long-duration journeys to Mars or the outer planets. Imagine a spacecraft traveling to Jupiter, powered not by finite fuel reserves, but by the limitless energy of the sun. It's a vision that could transform how we explore our cosmic neighborhood, making interplanetary travel more affordable and accessible. But the benefits don't stop there. Solar thermal propulsion also offers incredible versatility. By adjusting the size and configuration of the mirrors, engineers can tailor the system to meet the specific needs of a mission. Need more thrust for a quick maneuver? Focus more sunlight. Traveling through the outer solar system, where sunlight is dimmer, use larger mirrors to compensate. This adaptability makes it a promising option for a wide range of missions, from crewed expeditions to Mars to robotic probes, exploring the icy moons of Saturn. Of course, no technology is without its challenges. One of the biggest hurdles for solar thermal propulsion is scaling it up for larger spacecraft. While the concept works well for small probes or satellites, applying it to crewed missions or massive cargo ships requires significant advancements in materials and engineering. Then there's the issue of distance. As a spacecraft travels farther from the sun, the intensity of sunlight decreases, making it harder to generate the same level of thrust. To address this, future systems might need to incorporate advanced mirror designs or hybrid propulsion methods to maintain efficiency in deeper space. What makes solar thermal propulsion so exciting is its potential to revolutionize how we think about space travel. It's a reminder that the solutions to some of our greatest challenges might already be shining down on us, just waiting to be harnessed. By tapping into the power of the sun, we're not just building better engines, we're reimagining the very foundations of propulsion, turning the cosmos itself into a source of energy. As we look to the future, solar thermal propulsion stands as a testament to human ingenuity and our ability to find inspiration in the natural world. It's a technology that invites us to explore the solar system in a way that's both sustainable and innovative, offering a path to the stars that's as bright as the sun itself. And in doing so, it reminds us that the universe is full of untapped potential, waiting for us to reach out and seize it. The sun's energy could be the key to unlocking a new era of exploration, one where the solar system is no longer a distant frontier, but a place we can call home. Now, let's zoom in on a propulsion system that proves size isn't everything: pulsed plasma thrusters. These compact yet powerful engines might be small, but they pack a punch, making them perfect for small satellites and micro spacecraft. By harnessing short bursts of plasma, they offer a unique combination of precision and efficiency, proving that even the tiniest engines can play a big role in the future of space exploration. At the heart of a pulsed plasma thruster lies a simple yet ingenious process. When an electrical discharge is applied to a solid propellant, often a material like Teflon, it creates a burst of plasma, a superheated gas of charged particles. This plasma is then expelled at high speeds, generating thrust. Think of it like a miniature lightning strike, where each pulse creates a tiny but powerful push. The result is a propulsion system that's lightweight, reliable, and capable of delivering precise bursts of thrust when needed. It's a bit like a sprinter taking quick, controlled steps, rather than a marathon runner's steady pace. One of the standout features of pulsed plasma thrusters is their versatility. Because they operate in short bursts, they're perfect for missions that require fine-tuned adjustments, such as maintaining the orbit of small satellites or performing delicate maneuvers in space. This makes them ideal for CubeSats and other micro spacecraft, which are becoming increasingly popular for everything from Earth observation to scientific research. Imagine a fleet of tiny satellites, each equipped with a pulsed plasma thruster, working together to monitor climate change, track natural disasters, or even explore the moon. It's a vision that's as practical as it is inspiring, but the potential of pulsed plasma thrusters doesn't stop there. Their efficiency and compact size also make them a strong candidate for deep space missions. While they might not be able to propel large spacecraft, they're perfect for small probes designed to explore asteroids, comets, or even the moons of distant planets. By combining their precision with the endurance of other propulsion systems, pulsed plasma thrusters could help us unlock new frontiers in space, one small step at a time. Of course, no technology is without its challenges. One of the main limitations of pulsed plasma thrusters is their relatively low thrust compared to larger engines. They're not designed for rapid acceleration or heavy lifting, which means they're best suited for missions where patience and precision are more important than speed. There's also the issue of scalability. While they work beautifully for small satellites, adapting them for larger spacecraft would require significant advancements in design and power systems. But for the niche they fill, pulsed plasma thrusters are hard to beat. What makes these thrusters so compelling is their ability to do a lot with a little. They're a reminder that innovation doesn't always come in the form of massive engines or groundbreaking discoveries sometimes. It's about finding clever ways to solve specific problems. By focusing on precision and efficiency, pulsed plasma thrusters are carving out a unique role in the future of space exploration, proving that even the smallest systems can make a big impact. As we look to the future, pulsed plasma thrusters stand as a testament to the power of ingenuity and adaptability. They invite us to think differently about how we design and operate spacecraft, showing that sometimes the best solutions come in small packages. Whether it's keeping a satellite in orbit or sending a probe to a distant asteroid, these tiny engines are helping to push the boundaries of what's possible, one pulse at a time. Now, let's dive into a propulsion system that's quietly transforming the way we explore space: Hall effect thrusters. These compact yet powerful engines are a marvel of modern engineering, using electric and magnetic fields to create thrust in a way that's both efficient and versatile. Unlike traditional chemical rockets, which rely on explosive bursts of energy, Hall effect thrusters operate with a steady, almost serene push, a whisper of power that's perfect for long-duration missions. It's a technology that's already proving its worth in orbit, and it could play a key role in the future of space exploration. So, how do Hall effect thrusters work? At their core, they use an electric field to ionize a propellant, usually a gas like xenon, turning it into a cloud of charged particles or plasma. Magnetic fields then guide these ions, accelerating them to incredibly high speeds before expelling them out of the engine. The result is a steady stream of thrust, gentle but relentless, like a breeze pushing a sailboat across the ocean. While the force might seem small compared to the roar of a chemical rocket, the efficiency of Hall effect thrusters is unmatched. They can operate for years on just a few kilograms of propellant, making them ideal for missions where endurance and precision are more important than raw power. One of the standout advantages of this technology is its versatility. Hall effect thrusters are already being used in a variety of applications, from keeping satellites in precise orbits to powering deep space probes. For example, NASA's Dawn mission, which explored the asteroid belt, relied on Hall effect thrusters to travel between Vesta and Ceres, two of the largest objects in that region. This ability to sustain thrust over long periods allows spacecraft to reach distant destinations with minimal fuel, opening up new possibilities for exploration without the need for massive engines or heavy fuel tanks. But the benefits don't stop there. Hall effect thrusters are also incredibly precise, making them perfect for missions that require fine-tuned adjustments. Whether it's maintaining the exact position of a communications satellite or maneuvering a probe into orbit around a distant moon, these thrusters offer a level of control that's hard to match. And because they're so efficient, they free up valuable space on spacecraft for scientific instruments, life support systems, or even larger crews, making them a practical choice for both robotic and human missions. Of course, no technology is without its challenges. One of the main limitations of Hall effect thrusters is their relatively low thrust, which makes them less suited for missions that require quick acceleration or heavy lifting. They're also dependent on electricity, which means spacecraft need a reliable power source, often solar panels or nuclear reactors, to keep them running. And while xenon is an excellent propellant, it's also rare and expensive, prompting researchers to explore alternative gases like krypton or even water as potential substitutes. Despite these hurdles, the future of Hall effect thrusters looks incredibly bright. Advances in materials and engineering are steadily improving their performance, making them more powerful and durable than ever before. And as we continue to push the boundaries of space exploration, these thrusters are poised to play a central role in missions to the Moon, Mars, and beyond. They're a reminder that sometimes the most revolutionary technologies aren't the loudest or the fastest. They're the ones that work smarter, not harder. What makes Hall effect thrusters so compelling is their ability to bridge the gap between the present and the future of propulsion. They're a practical, proven technology that's already making a difference, while also offering a glimpse of what's possible as we continue to innovate. By harnessing the power of electric and magnetic fields, we're not just building better engines, we're redefining how we move through space, one ion at a time. And in doing so, we're opening up a universe of possibilities where the stars are no longer out of reach, but destinations we can power toward with quiet, relentless determination. Now, let's explore a propulsion technology that takes the raw energy of plasma and channels it with precision, magnetic nozzles. Imagine a spacecraft engine that doesn't rely on traditional mechanical components to direct its exhaust, but instead uses invisible magnetic fields to steer superheated plasma. It's a concept that blends the elegance of physics with the cutting edge of engineering, and it could be the key to unlocking the full potential of plasma-based propulsion systems. At the heart of this innovation is the challenge of controlling plasma, an ultra-hot, electrically charged gas that's notoriously difficult to handle. In traditional engines, plasma is expelled through a physical nozzle, but the intense heat and energy can damage or erode the nozzle over time. Magnetic nozzles solve this problem by replacing the physical structure with magnetic fields. These fields act like an invisible funnel, guiding the plasma flow without any material components touching it. It's like using an invisible hand to direct a stream of molten metal, ensuring it goes exactly where you want it to go, without melting anything in the process. The efficiency gains from this approach are significant. By eliminating physical contact, magnetic nozzles reduce wear and tear, extending the lifespan of the engine. They also allow for finer control over the plasma flow, enabling more precise thrust adjustments. This is especially valuable for missions that require delicate maneuvers, such as docking with a space station or maintaining a stable orbit around a distant moon. And because magnetic nozzles can handle extremely high temperatures, they're ideal for high-performance propulsion systems, like those used in plasma or fusion engines. One of the most exciting applications of magnetic nozzles is in next-generation plasma propulsion systems, such as the Wassermann engine we discussed earlier. By combining the power of plasma with the precision of magnetic fields, these systems could achieve unprecedented levels of efficiency and performance. Imagine a spacecraft traveling to Mars in weeks rather than months, propelled by an engine that's both powerful and durable. Or consider a deep space probe exploring the outer reaches of the solar system, sustained by a propulsion system that can operate for years without maintenance. Magnetic nozzles make these visions possible by addressing one of the biggest challenges of plasma propulsion, controlling the flow of such a volatile and energetic substance. But the potential doesn't stop there. Magnetic nozzles could also play a crucial role in fusion propulsion, another groundbreaking technology we've explored. In fusion engines, plasma is heated to temperatures rivaling those of the sun, creating thrust by expelling it at incredible speeds. Magnetic nozzles will be essential for directing this superheated plasma safely and efficiently, ensuring the engine operates at peak performance. It's a technology that bridges the gap between the theoretical and the practical, turning the immense power of fusion into a usable force for space travel. Of course, like any advanced technology, magnetic nozzles come with their own set of challenges. Generating and maintaining the strong magnetic fields required to control plasma is no small feat, requiring advanced materials and energy systems. There's also the issue of scalability. While magnetic nozzles work well for small-scale engines, adapting them for larger spacecraft will require significant engineering breakthroughs. But as our understanding of plasma physics and magnetic fields continues to grow, these hurdles are becoming more manageable. What makes magnetic nozzles so compelling is their ability to transform chaos into order. Plasma is one of the most energetic and unpredictable substances in the universe, yet magnetic fields allow us to harness and direct it with precision. It's a reminder that sometimes the most powerful tools are the ones we can't even see, forces like magnetism that shape the universe itself. By mastering these forces, we're not just building better engines, we're redefining what's possible in space travel. As we look to the future, magnetic nozzles stand as a testament to the ingenuity of human innovation. They invite us to imagine a world where the challenges of propulsion are met not with brute force, but with elegance and precision. And in doing so, they remind us that the cosmos is full of untapped potential, waiting for us to discover and harness it. The power of magnetism could be the key to unlocking the stars, one carefully controlled stream of plasma at a time. Now, let's step into a propulsion concept that feels like it's straight out of science fiction until you realize it's rooted in real science. Imagine a spacecraft that doesn't rely on rockets, fuel tanks, or even engines on board. Instead, it's propelled by a powerful laser beam fired from the ground, heating the air around it to create thrust. This is the fascinating world of Lightcraft, a technology that could revolutionize how we think about launches and even pave the way for rapid, cost-effective access to space. It's a bold idea, one that challenges the very foundation of traditional rocketry and opens up a future where launching into orbit might not require a rocket at all. At its core, a Lightcraft is a small, disc-shaped vehicle designed to ride on a beam of laser light. Here's how it works. A high-powered laser on the ground fires pulses of energy at the underside of the craft, heating the air to extreme temperatures. This sudden heating creates a shockwave, generating a burst of thrust that propels the vehicle upward. Think of it like a surfer riding a wave, except the wave is made of laser light and superheated air. As the craft ascends, the laser continues to fire, pushing it higher and higher until it reaches the upper atmosphere, or even space. It's a propulsion system that's as elegant as it is innovative, relying on external energy rather than heavy onboard fuel. One of the most exciting aspects of Lightcraft is its potential for rapid, low-cost launches. Traditional rockets are expensive, complex, and require massive amounts of fuel, much of which is burned just to escape Earth's gravity. Lightcraft, on the other hand, could drastically reduce these costs by offloading the energy source to the ground. Instead of carrying fuel, the craft would be lightweight and compact, making it easier and cheaper to launch. Imagine a future where small satellites or even cargo could be sent into orbit in minutes, powered by a laser array on the ground. It's a vision that could democratize access to space, making it more affordable for researchers, businesses, and even private individuals. But the potential of Lightcraft doesn't stop at Earth's atmosphere. Once the craft reaches high altitudes, the laser could continue to propel it through the vacuum of space by focusing on a reflective surface or using a different mechanism to generate thrust. This opens up the possibility of Lightcraft being used for interplanetary missions, offering a new way to explore the solar system without the need for traditional rockets. It's a concept that blurs the line between atmospheric and space travel, creating a seamless transition from launch to orbit and beyond. Of course, like any groundbreaking technology, Lightcraft faced significant challenges. One of the biggest hurdles is scaling up the system to handle larger payloads. While small, lightweight craft are well suited for laser propulsion, scaling the technology to launch heavier objects, like crewed spacecraft or large satellites, would require lasers of unprecedented power and precision. There's also the issue of atmospheric conditions. Factors like weather, turbulence, and air density can affect the laser's ability to generate consistent thrust. And then there's the question of energy. Powering a laser array capable of launching Lightcraft into space would require immense amounts of electricity, raising questions about sustainability and infrastructure. Despite these challenges, the promise of Lightcraft is too compelling to ignore. They represent a fundamentally different approach to space travel, one that shifts the focus from bulky, fuel-dependent rockets to lightweight, energy-efficient systems. By harnessing the power of ground-based lasers, we're not just building better launch systems, we're reimagining the very process of getting into space. It's a vision that invites us to think beyond the limits of traditional rocketry and embrace the possibilities of a future where the skies are no longer the limit, but a gateway to the stars. What makes Lightcraft so captivating is their ability to challenge our assumptions about what's possible. They remind us that sometimes the most revolutionary ideas come from looking at old problems in new ways. By turning the ground into a launchpad and light into a propulsion source, we're opening up a universe of possibilities, one laser pulse at a time. And as we continue to explore this technology, we're not just advancing science and engineering, we're redefining what it means to reach for the stars. Now, let's dive into a propulsion concept that merges the raw power of the stars with the practicality of rocket science: fusion-powered rockets. Imagine a spacecraft engine that doesn't just burn fuel, but taps into the same energy that lights up the sun, creating thrust so powerful it could slash travel times across the solar system. This isn't just a dream, it's a fusion of cutting-edge physics and engineering that could redefine how we explore the cosmos. At their core, fusion-powered rockets work by harnessing the energy released when atomic nuclei, like those of hydrogen, fuse together under extreme heat and pressure. This process, the same one that powers stars, releases vast amounts of energy, far surpassing what's possible with traditional chemical reactions. In a fusion rocket, this energy would be used to heat a propellant like hydrogen to incredibly high temperatures, creating a superheated plasma that's expelled at tremendous speeds to generate thrust. The result, an engine that's both incredibly powerful and highly efficient, combining the best of rocket technology with the limitless potential of fusion. The benefits of fusion propulsion are hard to overstate. For starters, it offers the kind of thrust needed for rapid interplanetary travel. Imagine cutting the journey to Mars from months to just weeks, or even days. Such speeds would not only make crewed missions to the red planet more feasible, but also reduce the risks associated with prolonged exposure to space radiation and microgravity. And it doesn't stop at Mars. Fusion-powered rockets could open up the outer solar system, making missions to Jupiter's moons, Saturn's rings, and beyond far more practical. It's a vision that transforms the solar system from a distant frontier into a place we can explore in detail within a single human lifetime, but the potential of fusion propulsion extends beyond speed. Its efficiency means spacecraft could carry less fuel, freeing up space for scientific instruments, life support systems, or even larger crews. This makes it an ideal candidate for long-duration missions, where every kilogram of payload matters. And because fusion relies on hydrogen, one of the most abundant elements in the universe, it offers a nearly limitless source of fuel, one that could be harvested from water ice on the Moon or Mars, making it a sustainable option for future exploration. Of course, the road to fusion-powered rockets is far from smooth. One of the biggest challenges is creating the extreme conditions needed for fusion to occur. On Earth, scientists have spent decades trying to achieve controlled fusion reactions, and while progress has been made, we're still far from a practical, compact fusion reactor that can fit on a spacecraft. Then there's the issue of managing the immense heat and energy produced by fusion, which would require advanced materials and cooling systems to prevent the engine from melting or failing. Scaling down these systems for use in space adds another layer of complexity, as does ensuring they're safe and reliable for crewed missions. Despite these hurdles, the pursuit of fusion propulsion is gaining momentum. Projects like the Direct Fusion Drive, a compact fusion engine being developed specifically for spacecraft, are bringing this technology closer to reality. These efforts are driven by the promise of a propulsion system that could revolutionize space travel, offering a way to explore the solar system and beyond with unprecedented speed and efficiency. What makes fusion-powered rockets so compelling is their ability to bridge the gap between the familiar and the extraordinary. They take the proven principles of rocket science and combine them with the immense power of the stars, creating a technology that's as practical as it is transformative. It's a reminder that the solutions to some of our greatest challenges might lie in the very processes that light up the universe. As we look to the future, fusion propulsion stands as a symbol of humanity's relentless drive to explore and innovate. It invites us to imagine a world where the vast distances of space are no longer a barrier, but a pathway to discovery. And in doing so, it reminds us that the stars are not just distant points of light, they're destinations waiting to be reached, powered by the same energy that fuels the cosmos itself. The journey to new worlds begins not with a rocket, but with the spark of fusion lighting the way to the stars. Now, let's journey into a propulsion concept that feels like it's been plucked from the pages of a science fiction novel, yet is rooted in real science: Antimatter-Catalyzed Fusion. What if we could combine two of the most powerful energy sources in the universe, antimatter and fusion, into a single, game-changing propulsion system? This hybrid approach might just hold the key to unlocking the stars, offering a propulsion method that's both incredibly efficient and mind-blowingly powerful. At its core, antimatter-catalyzed fusion works by using tiny amounts of antimatter to jumpstart fusion reactions. Here's how it plays out. Antimatter, when it comes into contact with regular matter, annihilates in a burst of energy. This energy can then be used to heat and compress hydrogen or other light atomic nuclei, triggering fusion, the same process that powers stars. The result is a chain reaction that releases immense amounts of energy, far greater than what's possible with traditional chemical or even nuclear reactions. It's like lighting a fire with a single spark, except the spark is a substance so rare and potent it could redefine propulsion as we know it. The potential of this technology is nothing short of extraordinary. For interstellar travel, where efficiency and speed are paramount, antimatter-catalyzed fusion offers a tantalizing solution. Imagine a spacecraft that could reach nearby star systems in a fraction of the time it would take with current propulsion methods. By combining the raw power of antimatter with the sustainability of fusion, we could create a propulsion system that's both lightweight and capable of delivering the thrust needed for such ambitious missions. It's a vision that transforms the vast distances of space from an insurmountable barrier into a challenge we can overcome, but the benefits don't stop at speed. Antimatter-catalyzed fusion is also incredibly efficient. Unlike traditional rockets, which require massive fuel tanks, this system would need only a small amount of antimatter to trigger the fusion process. This means spacecraft could carry more payload, whether it's scientific instruments, life support systems, or even larger crews, making it an ideal candidate for both robotic and human exploration. And because fusion relies on hydrogen, one of the most abundant elements in the universe, the fuel for this system could potentially be harvested from water ice on the Moon, Mars, or even distant asteroids, making it a sustainable option for long-duration missions. Of course, no technology this groundbreaking comes without its challenges. Antimatter is notoriously difficult to produce and store. Currently, it's created in particle accelerators like CERN Large Hadron Collider, but the process is incredibly expensive and yields only tiny amounts. Storing antimatter is another hurdle, as it annihilates upon contact with regular matter, requiring complex magnetic fields to keep it isolated. And then there's the issue of controlling the fusion reaction itself, which requires extreme temperatures and pressures to sustain. These are significant obstacles, but they're not insurmountable. Advances in physics, materials science, and engineering are steadily bringing us closer to making antimatter-catalyzed fusion a reality. What makes this concept so compelling is its ability to merge the extraordinary with the practical. Antimatter is one of the rarest and most powerful substances in the universe, yet by using it to catalyze fusion, we're harnessing its energy in a way that's both efficient and sustainable. It's a reminder that sometimes, the solutions to our greatest challenges lie in combining the best of what we know with the boldest ideas we can imagine. As we look to the future, antimatter-catalyzed fusion stands as a symbol of humanity's relentless curiosity and our drive to push the boundaries of what's possible. It invites us to imagine a universe where the stars are no longer out of reach, but destinations we can power toward with the energy of the cosmos itself. And while the road to this technology is long and filled with challenges, the rewards, unlocking the secrets of the universe and expanding the horizons of human exploration, are worth every effort. The future of propulsion might just depend on the rarest substance in existence, proving once again that the universe holds infinite possibilities for those daring enough to explore them. Now, let's venture into a propulsion concept that feels like it's been plucked from the pages of a science fiction novel, but is grounded in the strange and fascinating world of quantum mechanics, quantum entanglement propulsion. Imagine a spacecraft that doesn't rely on engines, fuel, or even the laws of classical physics as we know them. Instead, it harnesses the enigmatic phenomenon of quantum entanglement to potentially achieve faster than light travel. It's a concept so bold, it could rewrite the rules of space exploration if we can unlock its secrets. At its core, quantum entanglement is one of the most bizarre and counterintuitive phenomena in physics. When two particles become entangled, their properties are linked in such a way that measuring one instantly affects the other, no matter how far apart they are. This spooky action at a distance, as Einstein famously called it, seems to defy the speed of light, the cosmic speed limit set by relativity. Quantum entanglement propulsion seeks to exploit this phenomenon, suggesting that entangled particles could be used to transmit information or even propel a spacecraft faster than light. It's a tantalizing idea, one that could revolutionize our understanding of physics and space travel. The implications of this technology are nothing short of revolutionary. If quantum entanglement propulsion were possible, it could enable spacecraft to travel between star systems in a fraction of the time it would take with conventional propulsion methods. Imagine reaching Alpha Centauri, our nearest neighboring star system, not in thousands of years, but in days or even hours. It's the kind of breakthrough that could make interstellar exploration not just feasible, but routine, opening up the galaxy to humanity in ways we've only dreamed of. But here's the catch: quantum entanglement, as mind-bending as it is, doesn't actually allow for faster-than-light communication or travel, at least not in the way classical physics would suggest. While entangled particles appear to influence each other instantaneously, this effect can't be used to send information faster than light. The reason? The entangled state is random, and any attempt to manipulate one particle to send a message would break the entanglement. It's a limitation that's grounded in the very nature of quantum mechanics, and it's one of the biggest hurdles to making quantum entanglement propulsion a reality. Yet, despite these challenges, scientists and engineers are exploring ways to harness quantum entanglement for propulsion. One idea involves using entangled particles to create a kind of quantum bridge between 2 points in space, effectively bypassing the need to travel through the space in between. Another concept suggests that entanglement could be used to manipulate spacetime itself, creating shortcuts or wormholes that allow for faster-than-light travel. These ideas are still in the realm of theory, but they're pushing the boundaries of what we thought was possible, inviting us to imagine a future where the laws of physics are not just understood, but bent to our will. What makes quantum entanglement propulsion so compelling is its ability to challenge our understanding of the universe. It's a reminder that the cosmos is full of mysteries waiting to be uncovered, and that sometimes the solutions to our greatest challenges lie in the most unexpected places. By exploring the quantum realm, we're not just building better engines, we're redefining the very foundations of space travel, turning science fiction into science fact. As we look to the future, quantum entanglement propulsion stands as a symbol of humanity's relentless curiosity and our drive to explore the unknown. It's a concept that invites us to dream big, to imagine a universe where the stars are no longer out of reach, but destinations we can bridge with the power of quantum mechanics. And while the road to this technology is long and filled with challenges, the rewards, unlocking the secrets of the cosmos and expanding the horizons of human knowledge, are worth every effort. The quantum realm might just hold the key to the stars, and it's up to us to turn that key. Picture this: a spacecraft gliding through the vastness of space, not with roaring engines or glowing thrusters, but with the gentle pull of a long, unassuming cable. This is the essence of tether-based propulsion, a concept that turns the very fabric of the cosmos into a highway, allowing us to travel without the need for fuel. It's a brilliant reimagining of how we move through space, one that trades complexity for simplicity and fuel for ingenuity. At its core, tether-based propulsion relies on a simple yet profound principle: exchanging momentum with celestial bodies. Here's how it works. A spacecraft deploys a long, strong cable, often several kilometers in length, and uses it to interact with the gravitational or magnetic fields of planets, moons, or even other spacecraft. By swinging around these bodies or transferring momentum through the tether, the spacecraft can change its speed or direction without expending a single drop of fuel. Think of it like a cosmic slingshot, where the tether acts as the elastic band, flinging the spacecraft forward with the energy borrowed from the celestial body. It's a dance of physics, where gravity and momentum become our partners in exploration. One of the most exciting applications of tether-based propulsion is its potential for fuel-free travel. Traditional propulsion systems are limited by the amount of fuel they can carry, but tethers eliminate this constraint entirely. This makes them ideal for long-duration missions, where efficiency is paramount. Imagine a probe traveling to the outer planets, using tethers to swing past Jupiter, Saturn, and beyond, all without the need for massive fuel tanks. It's a vision that could make deep space exploration more sustainable and cost-effective, opening up new possibilities for missions that were once deemed too ambitious. But the benefits don't stop there. Tethers can also be used to stabilize spacecraft or generate electricity. By rotating a tether in Earth's magnetic field, for example, a spacecraft can produce power through electromagnetic induction, effectively turning the tether into a cosmic generator. This dual-purpose functionality makes tethers a versatile tool for space missions, offering both propulsion and power in a single, elegant package. It's a reminder that sometimes the simplest solutions can solve multiple problems at once. Of course, tether-based propulsion isn't without its challenges. One of the biggest hurdles is the durability of the tether itself. These cables must withstand the harsh conditions of space, including micrometeoroid impacts, extreme temperatures, and radiation, all while maintaining their strength and flexibility. There's also the issue of deployment. Unfurling and controlling a kilometers-long tether in the vacuum of space is no small feat, requiring precise engineering and careful planning. And while tethers are incredibly efficient for certain types of missions, they're not well suited for rapid acceleration or high-thrust maneuvers, which limits their use in some scenarios. Despite these challenges, tether-based propulsion represents a bold step forward in our quest to explore the cosmos. It's a technology that invites us to rethink how we move through space, trading traditional engines for the natural forces of gravity and momentum. By harnessing the energy of celestial bodies, we're not just building better spacecraft, we're learning to work with the universe itself, turning the cosmos into a partner in our journey. What makes this concept so compelling is its simplicity and elegance. It's a reminder that the solutions to some of our greatest challenges might already be out there, waiting for us to see them in a new light. As we continue to explore the potential of tether-based propulsion, we're not just pushing the boundaries of space travel, we're redefining our relationship with the universe, one tether at a time. The cosmos isn't just a place to explore, it's a highway waiting to be traveled, and tethers could be the key to unlocking its endless possibilities. Now, let's set our sights on a propulsion system that doesn't rely on engines, fuel, or even sunlight, but instead harnesses the invisible stream of charged particles flowing from the sun itself. This is the fascinating world of solar wind propulsion, a concept that turns the sun's constant outpouring of energy into a cosmic highway, offering a sustainable and fuel-free way to explore the depths of space. At its core, solar wind propulsion works by tapping into the solar wind, a stream of charged particles, mostly protons and electrons, that the Sun continuously emits into space. These particles travel at incredible speeds, often exceeding hundreds of kilometers per second, creating a flow of energy that permeates the entire solar system. A solar wind-propelled spacecraft would deploy a large magnetic sail, essentially a giant magnetic field, to interact with these particles. As the charged particles collide with the magnetic field, they transfer momentum to the spacecraft, gently pushing it forward. It's like sailing on a cosmic breeze, except the wind is made of charged particles streaming from the Sun. The potential of this technology is immense, especially for deep space missions where efficiency and endurance are critical. Imagine a probe traveling to the outer reaches of the solar system, propelled not by bulky engines or finite fuel reserves, but by the steady, unending flow of the solar wind. This makes solar wind propulsion an ideal candidate for missions to distant destinations like the Kuiper Belt or even the edge of the heliosphere, where traditional propulsion systems would struggle to maintain thrust over such vast distances. But the benefits don't stop there. Solar wind propulsion also offers a sustainable way to explore the cosmos. Unlike chemical rockets, which rely on finite resources, or even ion drives, which require propellant, solar wind propulsion taps into a limitless source of energy, the Sun itself. This makes it an environmentally friendly option for space exploration, reducing the need for heavy fuel tanks and freeing up valuable space for scientific instruments or life support systems. It's a reminder that sometimes the solutions to our greatest challenges are already out there, waiting for us to harness them. Of course, no technology is without its challenges. One of the biggest hurdles for solar wind propulsion is the relatively low thrust it generates. While the solar wind is constant, its density is thin, meaning the force it exerts on a spacecraft is small compared to traditional propulsion systems. This makes solar wind propulsion better suited for missions where time is less of a constraint, such as long-duration probes exploring the outer solar system. Scaling up the technology for crewed missions or larger spacecraft would require significant advancements in magnetic sail design and energy systems. Another challenge is the variability of the solar wind itself. Its strength and density can fluctuate depending on solar activity, such as solar flares or coronal mass ejections. This variability makes it difficult to predict and optimize thrust, requiring spacecraft to be equipped with adaptive systems that can adjust to changes in the solar wind. And as a spacecraft travels farther from the Sun, the solar wind becomes weaker, limiting its effectiveness for interstellar travel unless combined with other propulsion methods. Despite these challenges, solar wind propulsion represents a bold step forward in our quest to explore the cosmos. It's a technology that invites us to rethink how we move through space, trading traditional engines for the natural forces of the Sun. By harnessing the power of the solar wind, we're not just building better spacecraft, we're learning to work with the universe itself, turning the Sun's energy into a source of propulsion. What makes this concept so compelling is its elegance and simplicity. It's a reminder that the cosmos is full of untapped potential, waiting for us to discover and harness it. As we continue to explore the possibilities of solar wind propulsion, we're not just pushing the boundaries of space travel, we're redefining our relationship with the universe, one charged particle at a time. The Sun's power could be the key to unlocking new frontiers, offering a sustainable and innovative way to journey through the stars. Now, let's explore a propulsion technique that doesn't rely on engines, fuel, or advanced technology. It uses the natural forces of the solar system itself. This is the magic of gravitational assist, often called a slingshot maneuver. Imagine a spacecraft gaining speed not by burning fuel, but by swinging around a planet, borrowing a bit of its gravitational energy to fling itself forward. It's like a cosmic game of catch, where planets become the ultimate slingshots, propelling spacecraft to incredible speeds without a drop of propellant. At its core, a gravitational assist works by using a planet's gravity to alter a spacecraft's trajectory and speed. Here's how it plays out. As a spacecraft approaches a planet, it's pulled into the planet's gravitational field, gaining speed as it falls toward it. Once it swings around the planet, it's flung back out into space, carrying with it the extra momentum it gained during the encounter. The planet doesn't lose any energy in the process. It's simply a cosmic exchange, where the spacecraft borrows a tiny fraction of the planet's orbital energy. It's a brilliant example of working with the natural forces of the solar system rather than fighting against them. This technique has been a game changer for space exploration, enabling missions that would otherwise be impossible. One of the most famous examples is NASA's Voyager missions, which used a series of gravitational assists from Jupiter, Saturn, Uranus, and Neptune to explore the outer solar system. Without these planetary slingshots, Voyager 1 and 2 would never have had the speed or energy to reach their distant destinations. It's a testament to the power of ingenuity and the clever use of physics, turning the solar system's own mechanics into a propulsion system. But gravitational assists aren't just about speed, they're also about precision. By carefully planning these maneuvers, engineers can guide spacecraft to specific destinations with incredible accuracy. For example, the Cassini mission to Saturn used a series of gravitational assists from Venus, Earth, and Jupiter to fine-tune its trajectory, ensuring it arrived at Saturn with just the right speed and angle to enter orbit. It's a delicate dance of physics and planning, where even the smallest miscalculation can mean missing the target entirely. The beauty of gravitational assists lies in their simplicity and elegance. They're a reminder that sometimes the best tools for exploration are already out there, waiting for us to use them. Instead of building bigger engines or carrying more fuel, we can harness the natural forces of the solar system to achieve our goals. It's a sustainable, cost-effective approach that has opened up new possibilities for space exploration, from studying the outer planets to sending probes to the farthest reaches of the heliosphere. Of course, gravitational assists aren't without their challenges. The timing and precision required for these maneuvers are incredibly demanding, requiring meticulous planning and precise calculations. A spacecraft must arrive at the right planet at the exact right time and angle to achieve the desired boost, which means missions often take years or even decades to plan. And while gravitational assists are incredibly efficient, they're not a one-size-fits-all solution. They're best suited for missions to the outer solar system, where the gravitational pull of planets like Jupiter and Saturn can provide the necessary boost. What makes gravitational assists so compelling is their ability to transform the way we think about space travel. They're a reminder that the solar system isn't just a collection of planets and moons. It's a network of gravitational highways, offering a way to explore the cosmos without the need for massive engines or fuel tanks. By working with the natural forces of the universe, we're not just building better spacecraft, we're redefining what's possible in space exploration. As we look to the future, gravitational assists will continue to play a vital role in our journey through the solar system and beyond. They're a testament to the power of creativity and collaboration, where science and engineering come together to unlock the secrets of the cosmos. And in doing so, they remind us that the universe is full of untapped potential, waiting for us to discover and harness it. The planets themselves could be the key to reaching new worlds, offering a sustainable and innovative way to journey through the stars. Imagine a fleet of spacecraft so small they fit in the palm of your hand, yet capable of traveling to the nearest star system at a significant fraction of the speed of light. This isn't science fiction, it's the audacious vision of Breakthrough Starshot, a project that could redefine how we think about interstellar exploration. By combining cutting-edge laser propulsion with ultra-lightweight probes, this initiative aims to send tiny spacecraft to Alpha Centauri, our closest stellar neighbor, within a single human lifetime. It's a bold idea that trades massive rockets for miniature marvels, proving that the future of space travel might be small in size but colossal in ambition. At the heart of breakthrough Starshot lies a revolutionary concept, laser propulsion. Instead of relying on traditional engines or fuel, the project proposes using a ground-based laser array to propel a fleet of light sails, each no larger than a postage stamp, to incredible speeds. These sails, made of ultra-thin reflective material, would catch the laser beam like a cosmic sailboat catching the wind. The result, a spacecraft capable of reaching up to 20% of the speed of light, fast enough to cover the 4.37 light-years to Alpha Centauri in just over 20 years. It's a vision that transforms the scale of space travel, shifting from massive, fuel-guzzling rockets to nimble, laser-driven probes. But why Alpha Centauri? This star system, located just over 4 light-years from Earth, has long fascinated scientists and dreamers alike. It's home to Proxima Centauri, a red dwarf star with at least one confirmed exoplanet in its habitable zone, Proxima b. Sending probes to Alpha Centauri could provide unprecedented insights into this potentially Earth-like world, from its atmosphere to its surface conditions. Breakthrough Starshot isn't just about reaching another star, it's about answering one of humanity's most profound questions: are we alone in the universe? Of course, a mission this ambitious comes with its share of challenges. One of the biggest hurdles is the sheer scale of the laser array required to propel the probes. The system would need to generate a beam powerful enough to accelerate the light sails to relativistic speeds, yet precise enough to maintain focus over distances of millions of kilometers. Building such an array would require advancements in laser technology, materials science, and energy generation, a monumental task, but one that's not beyond the realm of possibility. Then there's the issue of durability. The probes must withstand the intense heat and radiation of the laser beam, as well as the harsh conditions of interstellar space, all while remaining lightweight and functional. Another challenge lies in communication. How do you send data back to Earth from a probe traveling at 20% of the speed of light, over 4 light-years away? The solution involves equipping the probes with incredibly compact, yet powerful communication systems capable of transmitting data across such vast distances. This would require breakthroughs in miniaturization and energy efficiency, ensuring that the tiny probes can send meaningful information back to Earth without running out of power. Despite these challenges, the potential rewards are immense. Breakthrough Starshot represents a paradigm shift in how we approach space exploration. Instead of focusing on large, expensive missions, it embraces the idea of small, scalable probes that can be mass-produced and launched in large numbers. This approach not only reduces costs, but also increases the chances of success. If one probe fails, others can continue the mission. It's a strategy that reflects the ingenuity and adaptability of human innovation, showing that sometimes thinking small can lead to the biggest breakthroughs. What makes Breakthrough Starshot so compelling is its ability to inspire. It's a reminder that the stars are not just distant points of light, but destinations waiting to be explored. By pushing the boundaries of laser propulsion, miniaturization, and interstellar communication, this project challenges us to dream bigger and reach further than ever before. It's a testament to humanity's unyielding curiosity and our desire to explore the unknown, no matter how far away it may be. As we look to the future, Breakthrough Starshot stands as a beacon of what's possible when we dare to think differently. It's a vision that transforms the challenges of interstellar travel into opportunities for innovation, turning the vast distances of space into a canvas for human creativity. And while the road to Alpha Centauri is long and filled with obstacles, the journey itself is a reminder that the cosmos is full of possibilities waiting to be discovered. The stars may be distant, but with projects like Breakthrough Starshot, they're closer than we think. Now, let's shift our focus from the engines themselves to the brains behind them. Picture a future where spacecraft aren't just powered by advanced propulsion systems, but are also guided by artificial intelligence, making decisions faster and more efficiently than any human ever could. This is the exciting intersection of AI and next-generation propulsion, a partnership that could redefine how we explore the cosmos. By combining the raw power of propulsion with the precision and adaptability of AI, we're not just building smarter spacecraft, we're creating a new era of intelligent space travel. At its core, artificial intelligence offers a way to optimize every aspect of propulsion, from engine performance to mission planning. Take engine design, for example. AI can analyze vast amounts of data to identify patterns and optimize designs, creating propulsion systems that are more efficient, reliable, and powerful than anything we've built before. Imagine an AI-powered engine that adjusts its thrust in real time, balancing fuel efficiency with performance based on the demands of the mission. It's not just about building better engines, it's about building engines that can think for themselves. But the potential of AI doesn't stop at design. Once a spacecraft is in flight, AI can take on the role of mission control, monitoring systems, and making split-second decisions to keep the mission on track. In the vast, unpredictable expanse of space, where communication delays can make real-time human intervention impossible, AI becomes an invaluable partner. It can detect anomalies, reroute trajectories, and even predict potential issues before they occur, ensuring that missions run smoothly even when millions of kilometers from Earth. This level of autonomy is crucial for long-duration missions, where the ability to adapt and respond to changing conditions can mean the difference between success and failure. One of the most exciting applications of AI in propulsion is its ability to manage complex, multi-system operations. Spacecraft are becoming increasingly sophisticated, with propulsion systems that need to work in harmony with power systems, life support, and scientific instruments. AI can act as the central nervous system, coordinating these components to maximize efficiency and performance. For example, on a mission to Mars, AI could balance the power demands of a plasma engine with the needs of life support systems, ensuring that every watt of energy is used effectively. It's a level of integration and optimization that would be nearly impossible for humans to achieve on their own. Of course, integrating AI into propulsion systems isn't without its challenges. One of the biggest hurdles is ensuring that AI systems are reliable and resilient enough to handle the extreme conditions of space. From radiation to temperature fluctuations, the environment outside Earth's atmosphere is unforgiving, and AI systems must be designed to withstand these challenges without failing. There's also the issue of trust. How do we ensure that AI makes the right decisions, especially in high-stakes situations? These are complex questions that require careful consideration as we move toward a future where AI plays a central role in space exploration. Despite these challenges, the potential of AI-driven propulsion is too significant to ignore. By combining the raw power of next-generation engines with the intelligence of AI, we're creating a new paradigm for space travel, one that's faster, smarter, and more adaptable than ever before. It's a vision that transforms the spacecraft from a passive vessel into an active participant in the mission, capable of learning, adapting, and even making decisions on its own. What makes this partnership so compelling is its ability to push the boundaries of what's possible. AI doesn't just enhance propulsion, it reimagines it, turning the challenges of space travel into opportunities for innovation. As we continue to explore the potential of AI in propulsion, we're not just building better spacecraft, we're shaping the future of exploration itself. The cosmos is no longer a distant frontier, it's a place where intelligence and ingenuity come together to unlock its endless possibilities. And in this future, the journey to the stars isn't just powered by engines, it's powered by the brilliance of human imagination, amplified by the limitless potential of artificial intelligence. From the quiet hum of ion drives to the mind-bending potential of warp engines, the future of space propulsion is nothing short of extraordinary. Over the course of this exploration, we've uncovered 30 groundbreaking technologies that could redefine how humanity ventures into the cosmos. These innovations aren't just incremental improvements, they're game changers, each offering a unique path to overcoming the challenges of distance, time, and energy. Whether it's the steady push of plasma propulsion or the audacious promise of antimatter engines, the possibilities are as vast as the universe itself. What makes this moment so exciting is the convergence of science, engineering, and imagination. We're no longer limited by the constraints of chemical rockets or the tyranny of the rocket equation. Instead, we're exploring propulsion systems that tap into the very fabric of the universe, from the energy of the sun to the mysterious forces of quantum mechanics. It's a testament to human ingenuity and our relentless drive to push boundaries, proving that the stars aren't just distant points of light, they're destinations waiting to be reached. As we stand on the cusp of this new era, one thing is clear: the journey to the stars is no longer a dream confined to science fiction. It's a tangible goal, one that could become a reality within our lifetimes. The technologies we've explored today are more than just ideas. They're the building blocks of a future where interstellar travel is not only possible but routine. Imagine a world where missions to Mars take weeks instead of months, where probes journey to distant star systems, and where humanity becomes a truly spacefaring species. That future is closer than you might think, but this isn't just about the technology, it's about what it represents. Each breakthrough in propulsion is a step toward answering some of humanity's biggest questions. Are we alone in the universe? What lies beyond our solar system? How far can we go? These are the questions that drive us, and the technologies we've discussed today are the tools that will help us find the answers. Now, it's your turn to weigh in. Which of these next-gen propulsion systems do you think will be the most revolutionary? Will it be the elegance of solar sails, the raw power of fusion, or the bold ambition of warp drives? Let us know in the comments. We'd love to hear your thoughts. And if you're as captivated by the future of space exploration as we are, don't forget to subscribe and hit the notification bell. There's so much more to explore, and we're just getting started. The journey to the stars has only just begun, and the best part, you're here to witness it. Together, we're not just dreaming of the future, we're building it. So, let's keep looking up, because the cosmos is full of possibilities, and the next great discovery could be just around the corner. The stars are calling. Will you answer?